Last time we stopped just the very last topic we discussed about was the curvature radiation. Now we began a sequence of processes which are very relevant, particularly when we move to considering relatively energetic photons. And in particular, we'll see that in the comparison between the rest energy of typical particles such as the electron and the photon's energy becomes comparable. So we see that other effects come into play and become dominant essentially. So the first of which is photoelectric absorption. I'm sure that you are somehow familiar with all of them, but we should see in a different light now. So that's my expectation. So the list of three processes essentially that we will go through today and also next week are in order: photoelectric absorption, which is relevant in many contexts, and first of all is the dominant process for absorbing photons, I would say typically below 1 keV. So when you are above, essentially, as we will see, photoelectric absorption becomes no more dominant. So, but below 1 keV can be really important, and in some astrophysical context, can be also the dominant processes for which, for example, in stellar interiors within stars, can be also the dominant process through which you can absorb photons. The second one is the Compton scattering, and essentially we'll see that this is the process that is the analog of the Thomson scattering that we've already seen, but in this case, the assumption that we made at the beginning when we studied the Thomson's cross-section, that the energy of the photon has to be negligible with respect to the rest mass, with respect to the rest energy of the electron, is no more the case. And in astrophysical context, again, this is the process that you can find within stars, and this is also relevant when you study X-ray binaries, so a compact object with an accretion disk, for example, which is very hot, as well as the accretion disk. So you have X-ray photons, and we'll see that very often one of the dominant processes in this case that contributes to the observed spectrum is related to Compton spectrum. The Compton process, as we will see today, is the process through which electrons can gain energy at the expense of photons. So photons lose some energy, and this energy is gained by electrons. There's also an inverse process, which is called inverse Compton. It's also very, very important in astrophysics. And we will see that this is the opposite case, in which you have ultrarelativistic electrons, which can boost photons through scattering. So in this case, who gains and who loses energy? The one who loses energy is electron. The one which gains energy is the photon. And also in this case, when you have particularly environments with intense radiation field and you have a lot of electrons, ultrarelativistic electrons, in this case you will see that some photons are so-called upscattered. Their energy is increased significantly, and we clearly see this effect within the spectra, so within energy of the photons as a function of frequency. And the last case is when the photon's energy becomes so high, so for example higher than the rest energy mass of the electron, much higher, better, in which the dominant process in that case will be pair production. And this process is important not only in an astrophysical context, but also when you consider interaction of high energy photons with matter, so with detectors. When you consider, for example, photons of some MeV energy, well, and interacting with some device, with some material, with some matter, with some detector, if your aim is just to detect these high energy photons, well, you have to know that we will see that, as a matter of fact, the dominant process by far is no more Compton effect, but is pair production. So whenever you have such high energy photons and they interact with matter, you're going to end up with the production of a pair of electron and positron. And one fair example of this case is, for example, the line that we see, the so-called annihilation line. We see a lot of within our galaxy towards the center. There is a strong annihilation line, which is the line corresponding to the rest energy of electrons and as well as positrons. So you have a lot of pairs, a lot of positrons which just annihilate with electrons, and so producing the photons whose energy matches the rest energy of the electron. And in that case, so one way to produce so many pairs is just because you have high energy gamma rays, which as soon as they interact, they make pairs. So this is just to give you an overview of the context and why these processes are so relevant in astrophysics, but not only in astrophysics. So let's begin this review by starting with the photoelectric absorption. So as you surely know, photoelectric absorption, also known as bound free absorption, if you compare it with the, for example, Bremsstrahlung, again in the parlance of atomic physics, you begin with a free electron, and you end up with a free electron. In this case, the situation is different. You have at the beginning one electron, which is in one state, in one energy level. So let's suppose we call EI as the energy level of some inner energy level of a given atom. Let's suppose we have a photon with energy h nu. Now, of course, in order for the electron to be ejected, you have to give it an amount of energy which is equal or greater than the binding energy. Otherwise, there's no way you can extract the energy. You can you can eject the energy. You can eject the electron. So just for energy conservation, the ejection of the electron corresponding to that energy level is only possible if you have a photon whose energy is greater, as I said, greater than the binding energy EI of the corresponding electron you have in mind. When this is the case, of course, you have to consider that both conservation of energy and linear momentum have to be fulfilled. So in that case, what happens? The photon is absorbed, and the electron just carries away the energy in excess. So what was the energy of the photon, h nu, minus the binding energy that was used just to eject the electron, and the remaining energy is essentially carried away by the electron in terms of kinetic energy. But in order to make sure that also linear momentum is conserved, you also need an atom. So overall, the photon is absorbed, and some of the energy and momentum are just split between the electron, which is ejected, and the atom itself. Otherwise, if you don't have the atom, there's no way you can just absorb the photon by both making sure that both energy and linear momentum are conserved. And so what happens when you study the corresponding cross-section of this absorption process of photons? Here you have a graph for a given element. Of course, it depends on the kind of element you're considering, just because, of course, the corresponding binding energies of the different energy levels change as a consequence. In particular, if we focus on the innermost energy level, so the one whose binding energy is the highest, so let's consider the innermost orbit, the innermost energy level of the electrons for a given atom. And this shell, so the shell of the corresponding shell, is also called K shell. And in this graph, the K shell, for example, of this element, which I don't remember, is this here. So what does this mean in terms of photoelectric cross-section. It means that when the energy, you see, is below the corresponding binding energy of this K shell, it means that if the energy of the photon is smaller, is lower than the K energy binding energy, there's no way, of course, for the conservation of energy that I just told you, there's no way the electron can be ejected. So you see that the photoelectric cross-section goes like this. But as soon as you consider photons whose energy is greater than the corresponding binding energy of the K shell, it means that all of a sudden, let me say this way, the probability of absorbing photons is a so-called edge. This is called just edge because you have a sudden increase in the photoelectric. As soon as you have more energetic photons, I would say photons which are energetic enough to eject the electron, you have a corresponding increase. And this kind of source of discontinuity just reflects the fact that you consider now photons which are just right above the threshold. And the energy threshold is nothing but the binding energy of the corresponding shell. If you consider outer shells, of course, the corresponding binding energy is smaller. So again, if you look at the second shell in which the binding energy is smaller, the so-called L edges, you see from a qualitative point of view similar behavior, depending on the different, of course, sub-levels that you might have. So the most for a given element, the edge with the highest energy, which is the one, as a matter of fact, which is most relevant in X-rays, is the so-called K edge. So this is due just to that, to the photoelectric effect. Photoelectric effect that I'm sure you remember, the one who first explained it was Einstein, once more, when he understood that photons' energy indeed scales with frequency. So no matter about the intensity of a beam, in order for the electron to be ejected, you have to consider a given frequency, so a sufficiently high frequency, not intensity of the beam. So this is just like that. Yes, this is something that I already told you. It's interesting to study the dependence of the photoelectric cross-section, for example, as a function of the most relevant quantities. One of which, for example, is the atomic number of the element. So what happens if I keep this photon with a given energy and I change elements? So in particular, I change the atomic number. We'll see that there is a huge dependence on the atomic number, as well as what we care about here mostly is the dependence on frequency. So by changing frequency of the photons, how does the photoelectric cross-section change as a consequence? So here we have to distinguish between the energy range of photons. So if you consider photons whose energy is clearly above the binding energy of corresponding to the K shell, for example, but still well below the rest energy of an electron. So in this case, the cross-section of the corresponding photoelectric effect, you see, has this formula here, where alpha is just the defined structure constant. Again, you see, what gives you the scale is, again, the Thomson cross-section. So that's why it's so ubiquitous, I would say. It's really important. And as I told you, you see the huge dependence on the atomic number. So when you want to, for example, to build up a detector, which is very effective in revealing photons, so you want something whose cross-section in the photoelectric effect case is relatively high. So you would you presumably would opt for a material with a relatively high atomic number. And then you also see the dependence on frequency. You see that there is a strong dependence on frequency in the sense of negative power law dependence. So when you increase frequency, the cross-section of the photoelectric effect drops very quickly. With here, the index is -7/2. So it's very strong. So it means that when you move up to increasingly larger energies of the photons, you should expect that the photoelectric absorption, so the capability of matter in this case to absorb photons, decreases significantly. And so this is also very important. And instead, when you move to somehow higher energy, so when it is no more the case that the energy of the photon is negligible with respect to the rest mass of the energy of the electron, the dependence on Z becomes a little milder, but not so much. You see, the power law index is still in the range between 4 and 5. So it's still a huge, strong dependence. This is, and in general, this is something that every physicist remembers. So the dependence of the photoelectric cross-section on both the atomic number and frequency. So I would also advise you for, regardless of any astrophysical context, this is also something very important, particularly when you are asked to evaluate as an order of magnitude, just see, okay, which is the dominant effect at some given, with some given material, within some given energy range of photons, which is the dominant process, which is responsible for photons absorption. Well, just remember that, and you immediately see you have all the ingredients to understand whether, for example, photoelectric absorption or Compton is dominant, as we will see when we will be talking about Compton. So let's move to a somehow more astrophysical context. Of course, if you consider a realistic case in which you have a gas with many different elements, each of which has its own cross-section, photoelectric cross-section, just because each element, of course, has its own K shell energy. So in this case, what you want to study is the resulting cross-section. So what we could call as the effective cross-section, what I call here as sigma nu E. E stands for effective. Effective in the sense that it takes into account the fact that you have a relative abundance for a number of elements. Here I put just a table in which you see the individual cross-sections for all the elements. You see the name of the element above. And so you see that, as I said here, the x-axis is a function of wavelength. So, and you see from high values to low values, just to show, so it's in terms of wavelength, but it from left to right is just by increasing frequency. And so you see, you have a lot of different energies. The different K edges are just different energies, and the higher Z, and of course the correspondingly higher the binding energy of the K shell. So here in this formula is just how we calculate the so-called effective cross-section of the photoelectric effect. Well, with sigma nu I, you consider the individual cross-section of the ith element. You consider that you have n elements, so the resulting cross-section will just be the sum, but a weighted sum, where the single weight, Ni, is just the relative abundance of the ith element. Of course, the more you have of one single element, and the correspondingly larger will be the relative weight of that element in the total resulting cross-section. And here the normalization 1 over NH, NH is just the relative the relative abundance of hydrogen. So it's a way to normalize the total resulting cross-section in with respect to the abundance of hydrogen. Why this is useful? Because then when you know the abundance, so for example, Ni is just, let's assume is just number of particles per unit volume. And of course, the same for Ni, so NH. Once you know the NH, so the number of hydrogen atoms per unit volume, by assuming a given abundance for all the other elements. So you automatically can express the abundance of, so the number density of hydrogen atoms times the effective cross-section. And this product, this guy, by this guy, is just equivalent to considering the effective. So the weighted sum of all the individual cross-sections. So it's just a way to define one single quantity. So the total, as I said, the total cross-section in units of relative to the hydrogen abundance, because hydrogen, of course, in an astrophysical context, is the most abundant gas, and so on. Ni and small ni can be just a relative abundance, so it can be also a dimensionless. While if we call capital NH the number density of H atoms, so well, you immediately see that just if you remember the definition of optical depth, the resulting optical depth of due to the absorption, photoelectric absorption to all these elements is just by definition of optical depth. So the integral of the along a given path dl of what? Of the absorption coefficient. And you remember that the absorption coefficient is the number density, in this case, of just hydrogen. Well, but it's equivalent to considering, as for the reason I just told you, all the the weighted sum of all the individual elements times what we define as the effective cross-section of the photoelectric effect. Of course, this is a function of the frequency, because this is specific. It depends on frequency. So that's why here the subscript keeps track of this. And given that we use the so-called effective cross-section, the resulting optical depth is, as a consequence, also a kind of effective. So what this means is that here, when you calculated the effective cross-section, you already assumed a relative abundance for each individual element with respect to hydrogen, essentially. So if you change the abundance, the relative abundance of all the elements that are responsible for photoelectric absorption, then of course you change, as a consequence, the effective cross-section, and as a consequence the effective optical depth. So all this is to emphasize the fact that when you know the number in a given region, for example, in which you have a source of photons and which you also have the possibility that photons get absorbed through photoelectric effect, when you know the abundance, the number density of hydrogen atoms, you can straight away calculate the corresponding optical depth due to photoelectric absorption. But you see that this assumes a given abundance, or I would say abundance pattern in the sense that for each individual element I assume a relative abundance with respect to hydrogen. So if you change this, as a consequence, all these and also the resulting optical depth changes. So typically what in astrophysics people do is, for example, assuming given standard abundances, one of which, for example, can be the solar abundance. So the relative abundance of elements that we observe in the sun photosphere. So we see, okay, you have all the abundance of each individual element in units of hydrogen abundance. So once you assume that, automatically this is equivalent to calculating the effective cross-section. And so for a given number density and for a given path, so for a given source, and this is encoded in this integral, you calculate immediately this guy here. Of course, the effective cross-section doesn't depend on the path along the so you can just take all the dependence on frequency just out of the integral. And you see that the resulting optical depth can be approximately described using this formula here, where you see I already replaced in the constant in just with numbers. So it means that, of course, well, in this case, energy, the energy of the photon is a unit of keV, which is the typical range we are interested in, and in which the photoelectric absorption is dominant. And this integral here, if you pay attention to the units, capital NH is in units of 1 over volume, number of particles over volume, so centimeter to minus 3. Integral in dl, so is centimeter to minus 2. And this guy here is also called column depth or column density, because if you imagine a column of with a unit area, this is just the number of photons that you collect in this column with a unit area. So number of atoms per unit area, essentially, that you get through a column which crosses a given source with a unit area, as I said. And of course, the more atom you have per unit per column density, and the correspondingly larger the optical depth. And then you know how the flux is suppressed. Once you know the optical depth, of course, you automatically know how flux is suppressed, and you know everything about then what you have to solve in terms of radiative transfer. So let's make an example, practical example, which is typical about values which are typical in astrophysics. Let's consider the length of a source, which is 1 kiloparsec, and 1 parsec is just 3×10⁻¹8 centimeters, so 1 kiloparsec is just 3×10⁻21 centimeter. Typical particle density, this value is typical in astrophysics in several contexts, which is 1 particle per cubic centimeter, so 1 hydrogen atom per cubic centimeter. Of course, you don't have just hydrogen, but again, that's a practical way to express all the. So assuming a given abundance, as I said, for example, solar abundance. So for each given, for any individual hydrogen atom, you have given numbers of other elements. You see that, okay, this guy here is just 1 times 3×10⁻21, so 3 times 2, you have 6×10⁻⁻1, so 0.6. So 0.6 is close to 1. So essentially, at which energy, when this guy is, when here h nu is right 1 keV. So in that case, you immediately see that you have an optical depth around 1 at 1 keV. Indeed, as I told you, the photoelectric absorption in astrophysical context is relevant, typical for energy at energies below 1 keV. Then, depending on this, it depends also on the typical column densities that we have, and indeed, 10⁻21 is typical for many sources. So, optical depth of 1 means that, of course, you start feeling the absorption. E to the minus optical depth, so a significant number of photons get absorbed through a source whose optical depth is 1. This is just the effective cross-section. Again, in the case of interstellar gas, in which some abundances are assumed, and you see that you can immediately recognize. So again, this is a weighted sum in which each element with its own K shell that you can distinguish through all these edges is strongly depending on the relative abundance. So it's not by chance that, again, here the x-axis is again the same units. So for example, you see that, well, in the case of hydrogen, you have just when the electron is just at the lowest energy level, you know that the binding energy is, if I remember right, is 13.6 electron volt. So in this case, the photon energy corresponding is around 912 angstrom. I remind you that 1 angstrom is 10⁻⁸ centimeter. So you see indeed that the K edge, if we call that of the hydrogen, is this one. Then of course the higher the atomic number, and the correspondingly higher with z squared the corresponding. So you see all the elements with the corresponding K edges. And here below, it's because these shouldn't be K edges, but should be L edges, I guess, just because they're least energy. The corresponding energy is lower. So you see, as a matter of fact, as I told you, the corresponding effective cross section as a function of the wavelength. And okay, let's see very practical examples in, again, astrophysical context of what's the impact of photoelectric absorption. So I just took power law spectra of sources that you will be you can know more about them if you will attend the course on multi-messenger astrophysics. But what these sources are? Well, these are gamma ray burst sources, and this is an X-ray spectrum of an X-ray source, which is the leftover in the hours, days after the explosion of the gamma ray burst. You have a decaying X-ray source, and we took a spectrum. In this case, the source was named. This is the name of the source. So the spectrum of the X-ray spectrum of the source is a power law. But you see that again, this is a log plot. So a power law is a straight line, as this guy here. But you see, when you move to lower energy, so when you, particularly here, you see when you go below 1 keV, which is here, you see that you have a drop in photons. Well, this drop is indeed due to the photoelectric absorption. And the dashed line that I show here is the power law spectrum that you would have in the absence of any photoelectric absorption. But as a matter of fact, assuming a given photoelectric abundance, relative abundance, element abundance, as a matter of fact, you see that the resulting absorption due to the increasingly larger optical depth, and this just reflects the fact that the lower the energy and the much higher the corresponding cross-section of the photoelectric effect. So you immediately see the effect. In this case, for your knowledge, the power law would be just a power law with the index -1. But again, this shaded area here is the amount of radiation that is just absorbed due to a photoelectric. And again, the fact that you can model this is the solid black line is just the model, where the red points are data. You see that you can satisfactorily model. So you immediately understand from the formula we've seen before that the optical depth scales with the column density. So by modeling the amount of absorption here, you can immediately estimate the column density. So how much stuff is along the line of sight. So you see, in this case, just by modeling this case, you immediately estimate a column density which is 5×10 to 21 centimeter -2. So this is a powerful way. Of course, if you make different assumptions, for example, you have theoretical reasons to assume a different abundance patterns. Of course, as a consequence, also the effective photoelectric cross section, and so optical depth changes as a consequence. And so, for example, you might see how this changes. And so this is an effective way to measure the column densities. So the amount of atoms that are that are surrounding the source of radiation, so in this case around the shear B source, or along the line of sight, because every atom which lies along the line of sight is in principle can in principle be responsible for photoelectric absorption. And so this is a very practical case to show you, once you know how it works, how it can be exploited to measure, in this case, a number density. So how much the density of matter along the path. This is another example from a paper of myself and other collaborators. Here, if you look at the range, a frequency range on the x-axis, you see there is a broad range. If you remember the frequencies associated with the spectrum, electromagnetic spectrum, you immediately see that here in this range, for example, is the optical and UV part. Here, rest means that it is in the co-moving frame of the galaxy which hosted this gamma ray burst, because when you are talking about gamma ray burst, you are talking about galaxies which are far away, so they are they are moving away from us due to the universe expansion. So we have to take into account of the cosmological redshift, something I already talked about in one of my first classes. So this is just correct, just like. But let's focus on the X-ray part. You see, the dashed line again is the power loss spectrum that you would measure in the absence of photoelectric absorption here. And here you have the absorption that you see here is due to dust, but this is completely different stuff. So let's focus here on the X-ray part of the spectrum. So again, you see this lack of radiation due to the absorption through photoelectric effect. You can again estimate the column density, which in this case is more or less similar to the amount of column density that we got in the previous example. Another comment is that if you look at the papers in the literature, typically you will see that the column density, so what is essentially this integral, so the integral of the number density along the path, along the line of sight, is sometimes just denoted by NH. So instead of integral NHDL, just NH. But it's a shorter way to express the very same quantity. So, but do not be confused by that. It's just a way of writing. But as in principle, one should express, one should mean number density integrated over the line of sight. Okay, so you might find that as a matter of fact, in the literature, you just find NH, capital NH. But it's important that you understand this in essence what this is, and this is just nothing but the column density. So, and this is all about photoelectric absorption. Moving on, let's talk about instead the Compton scattering. What is that? Well, this is just a scattering again between a photon and an electron at variance with what we already saw when we talked about the Thomson scattering. Here's the novelty, the new point is that the energy of the photons, which here I denoted with epsilon h nu, is no more negligible with respect to the rest energy of the electron, which was, if you remember, the assumption that we made when we were talking about the Thomson scattering. In this case, so, well, first of all, you have no photon absorption. The photon survives the scattering. And also, what about the electron? Well, in this case, the energy of the electron, we can consider the electron as a free electron. In many cases, we will see that, particularly when epsilon is much larger, is significantly larger than the rest energy of the electron. No, but it makes no difference whether the electron is a bound electron or a free electron, because when the binding energy becomes negligible with respect to the energy, so you can think, for example, of the outer shells electrons. So if the electrons belong to much outer shells, so the binding energy is correspondingly small, so it can be negligible, can be neglected with respect to the photon's energy. So you can consider, as a matter of fact, as free electrons, even if they're bound electrons. So the novelty here is indeed that you might consider very energetic photons. By very means, so no more negligible with respect to the rest energy of the electrons. And in this case, Compton scattering is also referred to as incoherent or inelastic scattering. Because the idea behind these names is that if you compare the energy of the photon before and after the scattering, you will see that the energy of the photon has decreased because some of its energy has passed on to the electrons. So you have a decrease of the photon's energy, so a decrease of the corresponding frequency, or if you want, an increase in the corresponding wavelength. And as a matter of fact, so you have a change in the wavelength. And so this is no more, from the point of view of the photon's energy, is no more, the energy of the photon is no more conserved, is no more the same, has changed. So that's why incoherent, just to point this out. So let's assume that the before scattering, prior to the scattering, we assume that the electron is steady, doesn't move. So it means that all its energy is just its rest energy. We call epsilon1 as the final energy of the photon. So nu1 is just the corresponding frequency, final frequency. For conservation of energy and momentum, which is what we are gonna apply in a moment, of course, in the most general case, you have to allow that both the electron and the scattered photon have different angles with respect to the direction of the incoming photon. So we just give names, and we call theta the scattering angle of the photon, so the angle between the incoming direction and the outcoming direction, as well as phi, the scattering angle of the electron. Okay, so now it's just a matter of course, for just conservation of momentum, you immediately realize that all these three vectors, so the momentum of the incoming photon, of the resulting photon, and of the final momentum of the electron, have to lie on the same plane. If this weren't the case, of course, you could not conserve the linear momentum. So they all lie on a plane in this case. So conservation of energy is just one scalar equation, and this is just the first equation. Let's see why. Well, epsilon is just the initial energy of the photon plus the energy of the initial energy of the electron, which is just its rest energy, so mc squared, plus the final energy, which is equal to what? To the final energy. The final energy is nothing but the final energy of the photon, which is epsilon1, plus, if we call p the linear momentum of the final linear momentum of the electron, well, you remember from relativity that, of course, the total energy of the resulting electron is this guy here, square root of this guy here. Inevitably, we have to apply special relativity because we are considering energies which are comparable or even greater than the rest mass energy of one particle. So there's no way, you have to use special relativity. And what about conservation? So the first equation is just conservation of energy, just like that. As I said, concerning conservation of linear momentum, we are in a plane. So we have to decompose, this is a vector equation. So in this case, in a 2D vector space, it means just two equations. These are, for example, let's consider the first one. The first one is the projection along the horizontal direction of the conservation of momentum. So these are all these terms in this equation are just momenta times the speed of light, because remember that, again, the relation between energy and linear momentum for a photon, there's just a factor of c, speed of light. So this, if we think of momentum, in this case, the initial momentum of is just due to the photon, because at the beginning the electron doesn't move, so has no linear momentum. And this is completely parallel to the horizontal direction. So it should be epsilon over c, okay? So here should be epsilon over c. What about after the scattering? Well, after the scattering, the photon has an energy epsilon1, but this is moving with an angle theta. So projecting along this direction, it should be epsilon1 over c times cos theta, which is, again, this guy here. Except for a factor of 1 over c, of course. And what? Plus, well, the horizontal component of the final linear momentum of the electron. But if we call p, we just call it p, so it is p cos phi, given that the angle in this case is phi. So if you multiply all the momenta that I just mentioned by C, you get just this here. I just immediately wrote this because it's handy to have all energies from a dimensional point of view. Okay. So let's apply the conservation of linear momentum in the perpendicular direction. Well, this is even easier because at the beginning you have no momentum at all in this direction, so 0. While in the final you have sine epsilon 1 over c sine theta, because you take this component here. And in this case with P, we denoted the modulus of the linear momentum. So we have to adjust the sign by hand, let me say. So you clearly see that in order to have conservation of linear momentum, inevitably, the figure here is not by chance. Inevitably, if the photon is going this way, the electron has to go this way down here. So inevitably, the perpendicular component will be just P sine phi minus again. And all this again has been multiplied by C. So let's have a look of all the unknown variables. And we have 3 equations. And what are the unknown variables? Well, you have epsilon 1, P, theta, and phi. So it means that there is no unique solution. What does this mean? Well, it means that any possible value, for example, of theta, in principle is possible. But once you fix theta, you immediately end up with a given solution. So it means that any theta in principle is possible to make sure that both energy and linear momentum are conserved. But once you consider one theta, then everything is automatically determined, because you have then, by fixing theta, you automatically have 3 equations and 3 unknowns. So you automatically know epsilon 1, phi, and P. Okay. So the essence is here that for any possible theta, there's a solution, and there's a unique solution for a given fixed theta. But in principle, every theta is possible. And then we will see that who's going to tell us about which theta is more probable. Well, that's a piece of information that it's the differential cross-section of a process, if you remember, that is telling us. Nothing is still said about this. We will see, as a matter of fact, the differential cross-section of Compton scattering. But for now, it's just a matter of making sure that both energy and linear momentum are conserved. So let's go through some simple algebra, but it's so important, this process, that it's worth spending a few minutes. So by just putting this guy, bringing this guy here on the left-hand side of this equation, and by squaring both sides of this equation, you immediately see that you end up with this guy here. Instead, if you combine the second and the third equation, for example, you take this guy here on the left-hand side term, this guy here on the left-hand side, and then you square both terms. Well, you see that you have here the same guy cos square phi plus sine square phi. So you have just P square C square plus, well, what you have from the second equation here squared plus what you have from the third equation. So this guy here squared, just like that. Oh, I foretell you here that the goal of the next calculations is just to find epsilon 1 as a function of epsilon, as a function of theta, and that's our goal. So to find as a function of the scattering direction how the photon's energy changes as a consequence. Okay, so this is the goal. So the ultimate goal that we want to pursue is just to find a formula which gives us epsilon 1 as a function of the remaining quantities. So, okay, if you just do that, of course, you see that cos square sine square just epsilon 1 square plus 1, and you are left again with the mixed product, with the double mixed product of this guy here. So minus 2 epsilon 1 cos theta. Now, if you replace this P square C square into this equation here, you see that, well, by just writing explicitly the square of this guy here, you have the square of all the 3 terms plus the 2 double products. So minus 2 epsilon 1, these 2 guys here, and then this guy here and this guy here as this one here. Equal what? Well, instead of p squared, c squared, you just replace this guy here, okay, which is exactly this guy here that I put you, plus mc squared all squared. So you see here a lot of terms that vanish. Epsilon 1, epsilon squared, epsilon 1 squared. You have on both sides as well as mc squared squared. So just by rearranging terms, for example, you can bring this guy here to epsilon 1 on the other side of the equation, and you bring and that's it. You're left with this equation here. So again, the goal, as I said, is to collect epsilon 1. So you bring this epsilon 1 on this side here. So by collecting epsilon 1, you see the first term is well, 2 has just gone. So epsilon 1 times 1 minus cos theta, in this case, plus epsilon 1, which plus mc squared, sorry. Equal to what? Equal to what is just left on the right-hand side of the equation, so epsilon mc squared. So you finally get the goal. So we have finally the formula which describes the Compton scattering. In particular, it tells you the energy of the scattered photon as a function of both the initial energy of the photon epsilon and the scattering angle. So let's have a look at this formula. You immediately see that depending on the scattering angle, but in general for any scattering angle, the denominator is always equal than 1. Well, the trivial case, if you consider, is when theta is 0. Well, if theta is 0, it means that the photon just didn't go through any scattering at all, essentially. Just it kept moving with the same direction and same energy. And indeed, you'll find that epsilon 1 is equal to epsilon. So this is not an interesting case. So whenever theta is different from 0, it means that the denominator is greater than 1. So it means that for any theta, the resulting energy of the photon, the final energy of the photon, is smaller than epsilon. So the photon has lost some energy. And of course, this energy has been gained as a consequence by the electron. And you immediately see that also there is the case in which there is the greatest gain by the electron is of course corresponds when you have the greatest energy loss by the photon. In particular, when you have a so-called head-on scattering. So when theta is just a pi, so it means that just scattered back, it scatters back. So there's a head-on scattering. So it goes this way and then finally just bounces back. In that case, you have the highest energy transferred from photon to the electron, because under this case, there's just a factor of 2. But you also immediately see that what gives you the scale, the amount of the scale of how the denominator can be larger than 1 is just this ratio. So the ratio between the initial energy of the photon and the rest energy of the electron. So immediately see that if you think carefully, in doing these calculations, we didn't make any assumption on the amount of energy of the photon. So in principle, we didn't exclude the possibility that the photon's energy is negligible with respect to the rest energy of the electron. So we didn't exclude the Thomson scattering, if you think. And indeed, if you think of a photon's energy, which is negligible with respect to the rest energy of the electron, indeed, it means that this ratio is a very small number. So 1 plus something very small is essentially 1. And you immediately see that indeed you recover what you expect. So the Thomson cross-section. So regardless of the scattering angle, when the energy of the photon is negligible with respect to the rest energy of the electron, you are in the Thomson case. And indeed, that means coherent scattering. That means that the photon's energy doesn't change essentially. There is also another way to express this formula here. Instead of using photons' energies, you can use the corresponding wavelengths, for example. So by remembering just the wavelength of a given photon is just c over the corresponding frequency. So by multiplying and dividing by h, so h nu in the denominator is just the photon's energy epsilon, and hc in the numerator, of course, you do the same for the scattered photons. So you call lambda 1 what is related to epsilon 1. If you replace, so instead of epsilon 1, hc over lambda here, and you do the same with epsilon 1, after some very easy calculations, you see that you end up with this relation. This is equivalent to this, just expressed in units in terms of corresponding wavelength. So lambda is the wavelength of the incoming photon, and lambda 1 is the final wavelength. So you see that you immediately see that the result of the Compton scattering is increasing the wavelength of the photon, because to the initial, you sum up to the initial wavelength some positive quantity. And the scale of the additional wavelength, I would say, is the so-called Compton wavelength of the corresponding particle. You see, it's just h over mc, so it just depends on which particle you consider. So in the case of an electron, which is the interesting case, you see that the Compton wavelength of an electron is just 2.4 10 to minus 2 angstrom. So it means that if you add to the wavelength something of the order of the Compton length, in order to see a significant change, it means that lambda has to be comparable with the Compton wavelength of in this case of the photon. Otherwise, so it means that whenever lambda is much larger than this guy here, it equivalently means that essentially lambda 1 is lambda, which again is equivalent to, say, Thomson scattering. So in order to see a significant change in the lambda, it means that you have to consider photons whose corresponding wavelength is comparable. Is not too large with respect to the corresponding Compton wavelength. Okay. So what about the cross section, in particular the differential cross section? So something that tells us how the scattering at any given scattering angle is, how probable that is. Well, this is given by something which I'm not going to prove, because this is something that you do from quantum electrodynamics, in which it would take us too far away, but that's not the point. I give you the result. The result here, theta is the scattering angle, the same angle that we introduced in the previous slides. And you see that this is quite symmetric. This is an easy way to remember. But mind that you've just seen, the ratio between epsilon 1 and epsilon is a function, is also a function of theta. So do not be confused. Here, the theta dependence is just hidden, goes through all these ratios, you see. So this is important to remember. And again, you see, you shouldn't be too much surprised to see that what gives you the scale is just something of the order of the sigma Thomson, so the classical radius of the electron squared. Why is this? Because when you are, well, this is correct at any, regardless of the energy of the photon. So it means that when you consider the range of the Thomson cross scattering, so it means that essentially when the energy of the photon doesn't change, you should recover what you already know from Thomson scattering. And indeed, let's see what happens. Well, if you look, this ratio is essentially 1. So 1 here in this term you have, here you have 1 plus 1, so 2 minus sine square. But if you take 1 plus 1 minus sine square, it's just cos square. So 1 plus cos square. But this should already look very familiar to you. This is nothing but the differential cross-section of Thomson's scattering in the case of unpolarized light. So you see how you recover what you really know. So this is kind of generalization to any possible energies of the photon, okay? So if you want to make the dependence on theta be apparent, you have to use the previous formula that we obtained and just replace with a ratio. And so you have you see immediately the full dependence on theta. Uh, Correspondingly, of course, if you want the total cross section, you have just to integrate over the sky the differential cross section. The result, again, this is called Klein-Nishina cross section, and so the resulting total cross section is just the integral of the differential Klein-Nishina cross section. And the result, which I'm not going to prove, it's a pretty scary formula, which of course you are not required to know by heart, unless a few details that I'm going to tell you right now. So you see that, first of all, again, the scale is given by the Thomson's cross section. Here, this x is a dimensionless quantity, which is the ratio of the energy of the photon in rest energy of the electron units. Okay. So in particular, when x is much smaller than 1, you should immediately recover what? What? Sigma t, if you remember, because you know the total cross-section in the case of Thomson's cross-section, which is indeed sigma Thomson. And indeed, the Thomson scattering regime corresponds to low energy photons. So it means that this x is much lower than 1. So let's have a look at this plot. So if we plot this function as a function of x, so as a function of the energy of the photon, well, the result is this one. I put just 2 plots, but they are equivalent, which allow me to make some comments. So first of all, you immediately see that at very low frequency, these are log-log plots. So you see that essentially the Klein-Nishina cross-section is nothing but the Thomson cross-section. And this is something you should already know, because again, this is nothing but the Thomson scattering regime. So for which you know everything about that. But you see something very important, and that's something what I would like you to remember, that when you start considering photons whose energy becomes comparable with the rest mass energy of the electron, and this plot here is, for example, more or less where this vertical dashed line. So you see that the total cross-section starts decreasing. And the more so, as long as you move to a corresponding increasingly higher frequency. So particularly when you consider Compton scattering and the frequency of the photon, the energy of the photons that you have in mind is larger, significantly much larger than the rest energy of the electrons. You see that the Thomson, the resulting cross section can be orders of magnitude smaller than our value 6.5, 6.7, 10 to minus 25 centimeters square, which is Thomson cross section. So you see practically, what does this mean? Well, it means that when you consider the probability for a highly energetic photons to be Compton scattered, well, that can be negligible, can be orders of magnitude less probable than the scattering that you would expect for in the case of Thomson scattering, for example, or for a much less energetic photon. So this is something very important to consider. So it means that when you move to considering increasingly larger photons, the so-called Klein-Nishina suppression of what? Of the cross-section, so of the corresponding probability for a photon to scatter an electron. And it's also useful to remember the behavior. It scales with frequency to -1 in this regime, when the energy of the photon is much larger than the rest energy of the electron, just decreases with frequency as nu to -1. So this is everything I would like you to remember. So this is very important, at least from a qualitative point of view, to remember that. So having talked about the Compton scattering, let's move to its brother, let me say. So it's the inverse Compton scattering, and this is really beautiful. Why? In this case, who gains and who loses energy? The roles are just swapped. Now you have an ultra-relativistic electron, which is here on the left side, on the left plot. So this is the so-called lab frame. So imagine just an inertial reference frame in which you have an ultrarelativistic electron. This ultrarelativistic electron at some point scatters with a photon, and this photon, the initial energy of the photon is again epsilon1, with whose linear momentum has an angle theta with respect to the direction, to the momentum of the electron. Okay, and as a result of the scattering, the resulting photon will have a different energy, which again we call epsilon1, with a different angle, which we call theta1. Okay, so 1 means after scattering. Now we will see that we will calculate the amount of energy which is now gained by the photon. So the ultrarelativistic electron upscatters the photon, up in the sense of increases the photon's energy. Instead, in the opposite case, of course, you can speak of downscattering when the photon loses energy. So this is interesting because this process is very important in many contexts, and it is useful to better understand what happens, to describe the same scattering in the comoving frame of the electron. So what is shown here on the right? So on the right, I consider a primed reference frame. So that's why I call the x, the same axis, x prime. So we consider a boost along x, given that x is the direction along which the electron is moving in the lab frame. So what connects the two reference frames is a Lorentz transformation with a boost along x. Okay, so it's interesting to see, to describe the scattering in this frame. Why? Well, in addition to being interesting, is also practical, because in this energy, in this reference frame, prior to scattering, the electron is steady, doesn't move. And so this is the case that we just considered in the previous discussion when we were discussing the Compton scattering. In particular, we discussed just what happens when a photon just scatters an electron, which can be considered as initially just steady. Still, so to give names, let's call, just following the convention that we adopt in many contexts. So if epsilon is just, in this case, the energy of the photon prior to scatter, we call epsilon prime the same quantity, the same corresponding quantity. So the energy of the photon in the electron comoving frame before scattering. And so we call epsilon 1 prime the final energy of the photon in the comoving frame of the electron. And again, theta prime will be the angle, the initial angle of the linear momentum of the photon with respect to the same direction, which is x1, x prime, prior to scattering, and theta 1 prime, the resulting angle of the final photon with respect to the same direction. Okay, and we call k the lab frame and k prime the comoving frame of the electron. So let's have a look at what happens. Well, we don't need to apply energy and momentum conservation. Of course, they have to, but we can just exploit what we already know in terms of Lorentz transformation and in terms of what we've seen about Compton scattering. So let's see. First of all, let's assume we know epsilon, so the initial energy of the photon in the lab frame. We want the corresponding quantity in the comoving frame. Well, if you remember, this is just a matter of applying to the momentum energy for vector of the photon. So it's just a matter of applying to the time-like component, which is the energy component of the forward momentum of the photon, Lorentz transformation. So given that the momentum of the photon in the lab frame forms an angle theta with the x-axis, and we are considering a boost along x-axis, epsilon prime is nothing but epsilon gamma times 1 minus beta cos theta. Lorentz transformation, where beta, of course, is related to the relative velocity, but the relative velocity is nothing but the electron's velocity in the lab frame, okay? And cos theta just comes from that, from the x component. You are just taking the x component of the linear momentum of the photon in the lab frame. Just Lorentz transformation, just like that. Now, let's assume we already calculated epsilon 1 prime. So the final photon's energy in the comoving frame. Now we have to get back to the lab frame. So let's suppose we know already epsilon 1 prime. We have to get back from the comoving to the lab frame. So it's just a matter of applying the inverse Lorentz transformation, if you think for a moment, which means, again, it's just equivalent to change the corresponding prime with the unprimed quantities and to change change sign of beta. So here you start with this guy here as an angle with respect to the x prime axis of theta 1 prime. So theta becomes theta 1 prime, beta becomes minus beta, and the energy of the photon that you have here is epsilon 1 prime. So epsilon 1 prime, and this is just epsilon 1 because you are getting back from the comoving frame to the lab frame. Again, inverse Lorentz transformation if you want. But you see, now the link is what relation lies between epsilon prime and epsilon 1 prime. So the initial and final energy of the photon in the comoving frame. But this is something that we already know. We obtained from Compton scattering. That's exactly the case here. In this frame, the electron was steady at the beginning, so we can just apply straight away this formula. With the caveat, look, here you have, if you think of this frame here, you have a plane. Well, a plane in general is automatically defined by two vectors. And here the two vectors are the x prime axis and the initial linear momentum of the photon. Well, the final momentum of the photon, there is no reason why this final vector should lie on the same plane, which is here the plane of the slide. There's no reason. Of course, I cannot make a 3D figure here. But you have to figure out that in the most general case, the resulting scattered photons, there's no reason why this vector, the linear momentum of this guy, has to lie on the same plane. In general, will be into a different plane. So, given that in this formula here, this angle is the angle between these two vectors, this one here and this one here, the scattering angle. So it's not this one here, because this, you have to imagine this vector that can enter or exit from the plane of the figure. In general, this is, and so that's why I use the capital theta, because this is a different angle. How can you calculate in principle? Well, as I told you, capital theta is the angle between these two unity vectors. So the unity vector of this linear momentum and the unity vector of this linear momentum. But if you have the two unity vectors, you want to calculate the angle between two generic unity vectors, just work out their scalar products, and you know very well that the scalar product between two unity vectors is nothing but the cosine of the angle between the two vectors. So the idea is just that. So the cos capital theta is the scalar product. You see here, I wrote the two unity vectors as triad of the three components. The three components are the three spherical components. If I consider the x prime axis as the polar axis, you see that the z component, so the polar component, is just the cosine of the angle between the corresponding unity vector and the polar axis. So let's have a look at the unity vector corresponding to this direction. So the unity vector along this direction, the angle formed with the polar axis is just theta prime. So cos theta prime. And this, in this case here, is theta 1 prime. So the third component, the polar component, is just cos theta prime. The other two components, so the azimuthal components, in this case, the x and y, in terms of this, of the spherical angle, well, if I call phi prime the azimuthal angle of this unity vector, so the angle on a plane which is perpendicular to the x prime, and phi 1 prime, the corresponding azimuthal angle of this unity vector, you see that the x and y component are sine polar times cos azimuthal angle, sine polar, sine azimuthal angle, and the same for both. So if we work out the scalar product, means this guy times this guy plus this guy times this guy plus this guy plus times this guy, it can be rewritten as this way. And indeed, if you are in the very special case that indeed this vector lies on the very same plane, well, in that case, it means that the two azimuthal angles are equal. So this guy is just 1. So indeed that you see that cos plus sine is cos of the difference between the two angles. And the difference of theta prime minus theta 1 prime is indeed this case. So indeed, this is the very special case in which all these vectors lie on the very same plane, and in which you clearly see that the special case is just the scattering angle is this angle here, which is theta prime minus theta 1 prime. Okay, so this is just to remind you that about the geometry of the scattering in the most general case. Okay, but let's have a look and let's consider one special case. The special case is when the scattering in the comoving frame of the electron is an elastic, so in the sense that it can be approximately considered as a Thomson scattering. But that means immediately, if you think for a moment, that the energy of the photon in the comoving frame of the electron essentially doesn't change. So it means that epsilon 1 prime is approximately equal to epsilon prime. That's the assumption that we make. And we will see the impact, the consequences of this assumption. So this is an assumption what we made. So we focus on the case in which the scattering in the comoving frame is essentially a Thomson scattering in the comoving frame. So let's see the consequences of this assumption. Well, that means inevitably that, of course, the initial energy of the photon in the comoving frame, so epsilon 1, has to be negligible with respect to the rest mass, with respect to the rest energy of the electron. Otherwise, you cannot have Thomson scattering. But if you remember from the previous slide, when you move from the lap frame to the comoving frame, you gain an extra factor of gamma. So let's just forget about the factor 1 minus beta cos theta. But the order of the magnitude when gamma is large is given by gamma. So epsilon 1 is of the order of gamma epsilon. So this condition, so in order for the Thomson scattering to be valid in the comoving frame, it means that the condition on the electron's energy, on the photon's energy, and electrons Lorentz factor in the lap frame has to be this. So in that case, of course, it means that the denominator is something very small, very close to 1. So for example, if you Taylor expand 1, when you have the denominator 1 plus something small, you can just consider it as a factor, multiplying factor 1 minus that something small, okay? And you know everything about Thomson scattering. So in particular, you know that the differential cross-section of Thomson scattering is, you remember this pattern of the kind of peanut shaped, you remember, 1 plus cos theta. But it means that essentially, apart from a factor of 2, if you consider the two extreme cases when cos theta, when cos square is 0 or when it is 1, so there is a factor of 2 at most, a difference between any two possible directions. So it means that essentially within a factor of 2, any possible direction, any possible scattering direction is equally probable, as I say, within a factor of 2. So it means that the scattering, the Thomson scattering taking place in the comoving frame of the electron, essentially the electron scatters off the photons more or less to any possible directions. As I said, within a factor of 2, with the same probability. And this is the key point of what we're going to see now. It means that when you get back, finally you have epsilon 1 prime, but epsilon 1 prime is more or less epsilon prime in this under this assumption. So when you get back to the lab frame, of course you have to do this. Just inverse Lorentz transformation, as I said. But you see, just because of the property of the differential cross-section of Thomson scattering, it means that in the comoving frame of the electron, more or less, photons will be scattered off to all directions. But it means that theta 1 prime can assume more or less any values with equal probability, within a factor of 2 with equal probability, I would say. So it means that, as a matter of fact, when you average out, it means that this guy can be considered as 0, averaging out. So it means that this guy is just comparable with gamma epsilon 1 prime, but epsilon 1 prime is just epsilon prime, because we are in the Thomson scattering regime in the comoving frame. But again, if you use the initial Lorentz transformation, epsilon 1 prime is epsilon gamma, the stuff here, which multiplied by gamma gives you an extra factor of gamma squared. But now, if you make no assumption on the incoming direction of the photon in the lab frame, so it means that you consider, for example, any possible directions of photons in the lab frame which are going to scatter the electron, it means that theta can be any value. So it means that when you average out, in general, you can neglect this factor when you consider a population of photons of any possible direction. It means that, on average, if you compare just the two quantities, you see, we are comparing two quantities in the lab frame. The final energy of the photon in the lab frame, epsilon 1, and epsilon, the initial energy of the photon. You see that the net result, on average, is a gain of a factor of gamma squared. And since we are talking about ultra-relativistic electron, it means that gamma can be orders of magnitude 10, 100, 10 to the third, 10 to the fourth. So it means that the energy gain experienced by photons can be very, very large by a factor of gamma squared. So when talking about, so not only in Compton scattering, you see that it is photons that gain energy at the expense of the electron, and that explains the name inverse. But you see that the amount of the energy gain is really huge, and the more so when you consider even more energetic electrons. In particular, this is something, so this square dependence of the Lorentz factor of the electron is something that you have to know, something that you have to remember for all your lifetime as a physicist. So whenever you are talking about inverse Compton, it means that you have considering ultra-relativistic electron which upscatters photons and which on average the energy gained by the photons scales with gamma squared. Okay, so you have an amplification of gamma squared times on average of the energy of the. So you see that if you think in terms of frequency, you can have photons which are relatively soft photons, and then as a result of the inverse Compton, they can be much higher, much more energetic photons. So let's summarize the key points of all this discussion. We started from lab frame, and we had that when you calculate the photon's energy from moving from the lab frame to the comoving frame of the electron, the energy increases by a factor. It increases. It is a factor of gamma larger. But within the comoving frame of the electron, you just have a change in direction. That's the work which is crucial in this case. And we will see in a moment what I mean. So the Thomson scattering in the comoving frame just changes the direction of the photon, but leaving its energy essentially unchanged. But now, when you get back from the commoving frame to the lap frame, you gain again another factor of gamma. So the net result is a factor of gamma squared. If this might sound to you as a kind of dodgy thing, you might say, well, you know that when you move from one frame to the other, you have to go through Lorentz transformation. When you get back, you have to get through inverse Lorentz transformation. So there is a factor of gamma in both ways, but this sounds like a dodgy thing, because you shouldn't. In the end, if you don't do anything on a photon, you just get back and forth between the two frames, just getting through inverse and Lorentz transformations. You should recover the very same quantity. Well, what is that? It sounds the very first time one sees this could be a little bit skeptical, could be left in wonder somehow. In some you could find it weird, but the key point that explains why there is nothing dodgy about that is this kind of sequences of. So let's see here. Here I just took a figure which I liked very much. So please imagine, instead of the space shuttle, there's the electron. Okay, so this is the electron, this is the lap frame, and this is in the lap frame. The photon, the electron is just moving within a given velocity. Here, all these red lines are just all the photons. For example, we assume that in the lap frame, as I said, you have an isotropic distribution of photons. So photons come from all directions in equal number. But if you move, and so theta is the angle that you use to describe the incoming direction of photons in the lap frame. When you move just still before scattering, so the first two figures just are about what happens before scattering, okay? So when you just consider the very same situation, just consider it now in the lap frame, well, in the commoving frame, sorry, just because of, you remember, relativistic aberration of light, or equivalently, relativistic beaming, you see that all these photons, as seen from the point of view of the electron, are just coming through within a cone whose semi-aperture angle is 1/gamma, most of them. So from the electron's point of view, all these photons will scatter within the cone. See, so almost the electron is gonna feel like most of them will scatter head-on. So almost head-on scatters, all of them. This is just due to relativistic beaming, or a relativistic aberration of light, call it as the way you like it, mode. But now let's stay within the commoving frame and let's see what happens across the scattering. But you see all these photons just coming to the electron this way, but now it's a matter of applying Thomson scattering. Thomson scattering tells you, well, within a factor of you remember the peanut-shaped differential cross-section, within a factor of 2, they will be scattered to any possible direction, more or less, as I said, within a factor of 2 with equal probability. So it means that the result after the scattering of all these bunch of photons will be more or less something more or less like this, more or less. But this is indeed a distribution of angles of theta 1 prime. So the angle of the photon after scattering, we are still within the commoving frame. You see, more or less will be scattered to all directions with the same energy of the photons within the commoving frame. Now, the final passage, the final step, is a matter we are interested in what happens in the lap frame. So we have to get back to the lap frame. But you see, now you have to, again, aberration of light, using again the Lorentz transformation. So it means that all this situation, almost isotropic distribution, when you get back to the lab frame, because again of relativistic beaming, this photon, I reminded, these photons are just traveling away from the electron. They have been just scattered. So these photons will be just traveling away in the lab frame within the 1 over gamma cone. So now let's have a look at the initial situation here in the lab frame and the final situation here in the lab frame. You have all photons that are just going to the electron, they're scattering off the electron, coming from all directions, and most of them will be upscattered within the cone of the relativistic beaming. So that should immediately make you more understandable why there is such a huge gain in energy. So you see that the key passage is here, is the capability of Thomson scattering in the moving frame of the electron of isotropize. You have an initial distribution which is nothing, everything but isotropic. Most of the photons are coming towards the electron as within a very narrow cone. But after the scattering, they will be scattered to all possible directions. And then when you have such a almost isotropic distribution, you have to get back to the lab, you have this gain here. So here, the Thomson scattering works as this isotropization process. So the capability of changing, of turning all these directions into any possible directions with comparable probabilities, then is the key to give you a net final gain in the lab frame of a factor of gamma. So again, it's possible also to use to express somehow to make further considerations. So for example, again, epsilon1, when you get back from here to here in the lab frame, once you know epsilon1 prime is again the stuff here, inverse Lorentz transformation, something that we already seen. But again, in the lab frame around the scattering, across the scattering, the energy doesn't change because we assumed Thomson scattering in the moving frame. So if you combine the two, it means that epsilon1 is just this guy here. But on the other side, epsilon1, again, using the Lorentz transformation, you can express the Lorentz epsilon prime as a function of epsilon this way. On the other side, when we started relativistic aberration, relativistic Doppler factor, if you remember, we could express the Doppler factor in both ways, depending on whether you use the angle in the moving frame or the angle in the lab frame, the moving frame or the lab frame. You remember there's this kind of symmetry. So it means that all this factor here can also be expressed as 1 over gamma 1 minus beta cos theta prime. If you don't remember this, you can just use the formula of relativistic aberration of light, which gives you the angle in the prime system as a function of the angle in the unprimed system. You just replace this into this, and you immediately prove this identity that I already reminded you. So if you work out this, you replace epsilon1 with this guy here, and instead of gamma plus, you make this guy here, you see that you end up with a formula which connects all the quantities in the lab frame. You have, if you look at this formula, you have all quantities in the lab frame, epsilon, epsilon1, theta, and theta1. And that is useful to make some easy considerations. So let's consider some very special case. So here I just copied the previous formula. So let's consider two extreme cases. So when you have indeed a head-on collision in the lab frame, I'm talking about. So head-on means that the electron is moving this way and the photon is moving the opposite way. It's just scattering head-on. So it goes like this, and then it is scattered, and it changes just 180 degrees change of the direction of photon. So it means that the incoming direction is just theta is pi radians, and the final is just upscattered. So changes direction by 180 degrees. So the final angle is just 1. Now, if you replace into this, you immediately see that this factor among brackets is just 1 plus beta minus 1 minus beta. But if you remember, we are talking about ultra-relativistic electrons. So if you, again, Taylor expand beta as 1 minus 1 minus 2 gamma squared, well, in this case, beta here, you don't have to Taylor expand. Beta is just 1, so 1 plus 1 is 2. In this case, this is useful, 1 minus 1, so you're left with, in the denominator, with 1 over 2 gamma squared. And so 2 times 2, 4 gamma squared. So you see that in the head-on case, you have the highest possible gain. Remember, in the previous case, we told the gain is of the order of gamma squared epsilon. Well, we see that in the very special case in which we have the photon has the maximum energy gain, this factor is a factor of 4. So the maximum increase is 4 gamma squared times epsilon. In the opposite case, well, the opposite case is when the photon chases, so it collides with the electrons from below. So it's just the opposite angles. So you immediately see that this is just the reciprocal, essentially, of that case. In that case, you have this is one of the few photons which are particularly unlucky, because in this case the photon loses energy because it just scatters off the electron from behind. So as a matter of fact, the resulting energy is suppressed by a factor of 4 gamma squared. So these are the two extreme cases. Okay, so I think that I already said a lot of things. I think I'm going to stop here. Do you have any questions? Okay, so let me stop the recording.